Thanks for joining me at Paper Club. So yeah, I thought today I'll present a paper which I kind of found through my mailing lists, and I think just appeared in my mailbox, but I just thought it was quite a cool paper, and I chose it because it's got this supposed connection to how human brains process information and perform reasoning, and I personally like biologically inspired technologies. So the paper is called Hierarchical Reasoning Model, and is by Sapient Intelligence, which I think is a sort of AI company from Singapore. And the what's the kind of high level thing about the paper? It's authors want to improve reasoning in models. They take a biologically inspired approach to that, which is to try and segment reasoning into these high level and low level processes. And then the results are actually quite promising with this, because they're able to outperform state-of-the-art models like Claude 3.7 or O3 from OpenAI, with only 27 million parameters at some of these like really hard reasoning benchmarks. So they construct their own benchmark first, which is a combination of like really complex Sudoku puzzles. There's also pathfinding, and then the main one, which is I think the ArcAGI, which seems to be like a very popular benchmark for LLMs to at least guide the thinking into whether the model exhibits any sort of artificial general intelligence / really good reasoning. So yeah, so really promising results on this paper. So I thought it'd be worth exploring it. Yeah, so maybe I'll start with kind of the high-level problem. So what the paper is trying to do is, as I said, improve reasoning in these language models. But this is quite hard to solve. There's many companies that are continually working on that. You can see sort of the thinking modes in OpenAI models, in Claude models. However, things like that and chain of thought in general have issues. First of all, it's like high latency. Second of all, is curated data requirements. So you need curated data to train these models to behave in that way. And then you've got brittle task decomposition. So you don't really know how that task will be decomposed to then perform the reasoning. And another kind of interesting thing that they point out is LLMs in general have a shallow architecture, which means with the depth of the architecture being quite fixed. And for the first part, I was like, what do you mean shallow architecture? They're deep neural networks. By definition, they're deep models, not shallow models. But what they actually mean is that the depth of them is fixed, which means depending on the tasks, the depth of the model does not increase or decrease. Which in this kind of classification of complexity classes of Boolean circuits, for example, that means it prevents the model or prevents the circuit from performing or solving problems that require polynomial time. So I thought we'll start with that, and we kind of explore what that means, what they mean, what's the motivation for the paper. So I prepared a few slides. So we'll start really kind of basic with logic gates and the computational complexity classifications. So I don't know how many of you are aware of like this computational complexity theory, but in general, it's this big O notation. So you've probably seen like O of n, O of log n. It basically tells us how much time or resources are needed to solve a problem computationally, typically in terms of this input size n. So O of 1 will be constant time, so it doesn't matter how many items you're processing, you're always going to process them in the same amount of time, or memory. O of n is dependent on the number of inputs, and then O of log n, it's the complexity is related to the input size logarithmically. So we can further classify these into categories that basically group these problems. Or they're also kind of defined by the resources needed, and more specifically by the circuit depth. But what they mean by circuit depth is they're thinking about this problem in a sense of Boolean circuits, in sort of logic gates, in integrated circuits, in processors, etc. So they propose these two. Well, they bring out these two classes, which is AC0 and then TC0, which are classifications for complexity of circuits. And they model kind of shallow and constant depth computation, similar to what they say about LLMs. So to kind of start with this, we can think about a small refresher of Boolean logic. So you can think of Boolean values as they're either false or true. We've got these operations, which are basic rules for how you combine these values. So we've got like a not, which basically flips the value from 0 to 1 or from 1 to 0. It's an inversion. We've got an and, which is true if both A and B, two values are 1, then the result of that operation will be 1. And then we've got or, which is true if at least one of A or B is 1. So you can see that what we call a truth table here. If 0 and 0, that means and does not satisfy because neither of them, like both of them would have to be 1. And then neither of them is 1, which means or is also is not satisfied. So it's a kind of very simple logic Boolean table. There's various different logic gates out there. There's like these nots, ands, nands. Usually nands are used for like memory. Yeah, so various different types of gates. They do slightly different things. So based on their inputs, you can get different outputs. And Boolean circuits are basically combinations of these gates. And you can have these like measures of the circuit, which one of them is the depth, is how many gates does a signal pass through. So in this case, it's 2. And then these two gates, basically, this one is an OR gate, and this was an AND gate. You can see that this circuit will first pass through the OR gate, and then the result of these A and B OR will go into the AND gate and combine with C. So we've got 2 layers in terms of depth, one OR layer and one AND layer. So this is another example, which is like a very simple adder. So you can see that in order to perform higher level kind of computation or more complex computation, the width of the circuit isn't as important as the depth. So that it's the depth that actually unlocks the more complex capabilities. So in here, in order to actually perform a full addition in base 2, so in Boolean values, you actually need 3 layers here. So we first go through this XOR, then and then 3 and OR. So the maximum depth here is 3. So this is what they point out, which is AC0, which is the classification of circuits, which they compare LLMs to, are not complex enough in order to be able to perform like global compute global properties like parity, whether the number of ones is odd or even. They have a constant depth, and they've got a polynomial size, which means the number of gates actually grows reasonably with the input size. However, the depth doesn't. So yeah, it's unbounded finite, which means the gates can take as many inputs as you want. For example, you can have 100 inputs into one OR gate. But that still does not unlock the complexity of the capability. We've got these other ones, which I mentioned, which are TC0 threshold circuits, which kind of slightly expand upon. Oh, yeah, sure. That better? Nice. We've got a question, I think. Yes, I think we have a question.
Yeah, I don't think we can't hear you, Arshad, if you're saying something. Maybe you can type it in the chat.
Yeah, okay. So I'll continue with this. So we've got this other type of threshold circuit, which expands upon these AC circuits that and includes this threshold gate, which basically you get an output worth 1 if the weighted sum of all the inputs is higher than a certain threshold. But there's still constant depth and there's still polynomial size, although they're more powerful. So you can add parity, majority, and simple addition. So why does this matter for LLMs in reasoning? So I think what they're trying to connect here, the authors, is that transformers have a fixed depth of layers once they've actually been trained, and they excel at this pattern recognition and very parallelizable tasks, but they struggle with problems that require these long chains of reasoning, which kind of prevents them from doing from like proving theorems, performing long division, planning very far into the future, and this resembles this constant depth circuits. So they process inputs in parallel, but they can't grow their reasoning depth. And the last one is the idea is the Turing completeness. So by default, a system is Turing complete if it can simulate a Turing machine, which means it can compute any computable function given enough time and memory. So you've got programming languages and CPUs, which are very Turing complete. But these classes of circuits, and therefore LLMs, they belong to these shallow classes, and they're not inherently Turing complete, which means they cannot perform these tasks requiring polynomial time in a scalable way. So we've had these like odd workarounds. So you've seen probably this in like agents. We've got scratch pads, we've got tool use, we've got chain of thought, which are all kind of crutches to try and add more reasoning capability to an inherently kind of inherently incapable architecture for performing reasoning. And these we've also got RNNs, which allow you to have recurrence. And then we've got other like hybrid neurosymbolic methods that combine neural nets with some like specific algorithmic modules that have been defined. So I'll have a look at the question. So yeah, does the iterative nature de-docking not help at all, or they think it doesn't help with the complexity of the problem? No, they actually do think that the iterative nature of what they're proposing is helping with the complexity of the problem, but not the iterative nature directly of the coding, for example, of how transformers work. So what they're saying is basically the model doesn't have unlimited depth when it's just a basic transformer, but what they're proposing is allowing that model to, in theory at least, get unlimited depth. Cool. So that's kind of the preface to this, and I make this a bit bigger. So yeah, it's a hard problem to solve. We've got these computational complexity classes. LLMs are not Turing complete. And then what they do is they try making quite a few analogies with brains and how brains work. So for example, in brains, language is only a tool for communications. It's not a tool or a substrate for thought. Brains also sustain long reasoning chains in this latent space, so something that we cannot easily observe, without translating back and forth through language. So how can we achieve the similar thing with a language model or just a model? So we've got things like recurrent architectures, which allows us to increase the depth of basically computation in such a model, so typical RNNs. However, they basically need backpropagation through time, which means they will unroll the computation in order to be able to calculate the gradients for training. And that is really computationally expensive because you have to, the number of time steps that you set is the number of states that you need to capture and calculate gradients for in order to backpropagate through time as these steps unroll. So they also say that this is biologically implausible, that they don't think that this is how the brains work and how reasoning in usually in human brains work. Yeah, so brains, as they describe, work by hierarchical computation in different regions at different timescales. So we've got the slow sort of high-level analytical circuits that integrate the information across longer timescales and form kind of abstract representations of information. And then we've got these fast, low-level circuits that basically do like immediate, detailed, and processing, and they process sensor information, they control movement for motor execution, so that they're much more kind of here now, and then fire and forget. whereas these slower ones are more longer timescales, and that's how they work. The important thing, I think, is the temporal separation here. So I can't remember exactly where they've put that, but yeah, where they've put that. But essentially, what that means is these two circuits in the brains, they operate in different, what they call neural rhythms. So you may have heard about brain waves. So these slower circuits operate on theta waves, which are between like 4 and 8 hertz, whereas these faster circuits operate on these gamma waves, which are between 30 and 100 hertz. So we've got this stable high-level guidance, and then we've got this rapid, unstable, low-level processing that can really quickly change. So how do we translate that, and what's the sort of high-level approach to this that they've taken? So they proposed this hierarchical reasoning model architecture where you've got two modules. You've got this high-level module and low-level module. Very kind of mapped to what I just described about brains. Abstract, deliberate reasoning for the high level, and fast, detailed computation for the low level. And yeah, so that's how they're trying to do this. Now, they have to battle the problem. Both of these modules, just to add, are RNNs. So they have to battle the problem of backpropagation through time. So what they do is they actually approximate it. So they propose this method of one-step approximation for training these models, which eliminates that requirement for backpropagation through time, and in that eliminates the credit assignment problem, which is basically like which internal components, which are these neurons, weights, layers, or time steps, that were actually responsible for correct or incorrect output. So you don't have to care about that. So for shallow networks, normally this is quite straightforward. So you can see the error at the output of the model, which can be traced back quite easily. Whereas for these deep or recurrent networks, it's not as easy. It's actually quite hard and computationally expensive to try and compute that. So we've got the so what they're claiming is that actually you can get a O of 1 complexity through this approach versus O of t for t time steps for the usual like backpropagation through time, which is really interesting because I've not seen any other architectures that would claim that before. What's another interesting thing about this model is that it only took them 1,000 input-output examples without any prior pre-training or chain of thought supervision on any other fine-tuning to basically surpass and state-of-the-art in these quite hard benchmarks. So they did the Sudoku puzzles, and you can see that with only 27 million parameters and much less tokens actually given in context, they've achieved like 40.3% on RKGI. I think it's RKGI, yeah. Which surpasses like O3 Mini or Claude, which is, these models are like 150 to 250 billion parameters. So it's a huge kind of gap of the parameter size versus what these models can actually do. So really promising. So yeah, I thought might be good to discuss this paper because of the results that they're claiming. Nice thing is they also provide code. So full code is here, and in just under a month, they've had like 10,000 stars on GitHub, which kind of shows that people are interested. That can be a bit misleading because that doesn't mean that this actually works really well. It just means that people are hyped up about it. Nice. Okay, so that's kind of the high level of how that works. Where can we go next? So talked about the results. Yeah, so how does that work? We've got these 4 different components in this network. We've got this input network, Fi. We've got the low-level recurrent module, FL, high-level recurrent module, FH, and an output network, which is FO. This low-level, both of these are RNNs, as the authors claim, but I actually thought they're not exactly RNNs, they're transformers. So I'm not sure how and why they described them as RNNs when I looked into the code, but maybe I missed something there. But anyway, basically, like black box modules that you can think of that are trainable, and they have some hidden state, like ZL for FL, and then ZH for FH. And they're all initialized with these vectors, respectively. So the way this works is that we have some n number of cycles. These are the high-level cycles. And then we've got t low-level time steps. So overall, we perform like these n times t steps within a single forward pass of this network. So the process is that we project the input, so x, through this network, and that gives us this x squiggly. And at each time step, we would perform an update of the L module of its own state, conditioned on its previous state, the current state of the high-level module, which is fixed in that specific cycle, and then the input representation and some parameters for the low-level module. So that kind of gives us the hidden state of that module. And then at each cycle, which is this kind of, you could think of it as the outer loop, we've got the H module, which will then perform this update given the last known state of the L module. So you can think of, if the low-level module performed 5 iterations, it will take the result of the last 5th iteration, and it will incorporate that as an update to the state of the high-level module. So the high-level module only really looks at the last hidden state of the low-level module. Yeah, and finally, after n cycles, we get the prediction y hat, which is extracted from the hidden state of the H module. Yep, single forward pass. They also talk briefly here about this halting mechanism, which is detailed more later on. Well, first, they talk about this idea of hierarchical convergence. So they talk about how standard RNNs are kind of fundamentally limited because they try to converge too early. So as the hidden state settles kind of towards some fixed point, the update magnitudes for RNNs, they actually shrink, which means it stalls computation and it reduces the effective depth. And that's what they show here on these diagrams. So when you look here, that a typical recurrent neural net, just for reference, this is showing the forward residuals of this network, so of these networks. So for recurrent neural nets, at the very beginning, these are the quite large residuals, and then they pretty much immediately drop and then flatline. For deep neural nets, the beginning and the end of the layers are the most affected, whereas for what they're proposing is that the high-level module is continuously kind of reducing its almost error, and then the low-level module will kind of restart its operation throughout. So the high-level module controls the overall progress towards a goal, whereas the low-level module will do these like almost branching out of in reasoning throughout the process, because it will essentially be reset on every iteration of the high-level module. So, yeah, this is why they got this sort of graph here. So they use this forward residual as like this convergence measure. So the idea is that like each step of this model is trying to sort of refine its hidden representation towards some solution, and they call it the equilibrium. And this forward residual basically quantifies the mismatch between the current state and the equilibrium that the dynamics are kind of pushing it towards, was how I understood. So if a small residual, the system is close to convergence. Large residual, the system still has significant sort of updating left to do. Yeah, so we've covered the RNNs, DNNs, and this proposed hierarchical reasoning models that behave differently in that when observed under that sort of regime. So nice. So the next bit would be the important thing is the in each cycle we get this fresh context for the L module. So essentially what happens here is like you can think of each of these drops here as like the model that the low-level module is tending towards some equilibrium. It gets restarted, tends to some other local equilibrium, gets restarted, tends to some other one, but eventually it will arrive at a similar location to where the high-level module is. Wait, no, they didn't talk about how they translated that. I'm not quite sure. Maybe there's something in the code. I didn't really. I think majority of it is just the actual code for the model, but nothing to do with the with these. Yeah. So the important thing is this context for this low-level module gets reset on each iteration. And then finally, like, how do we get to this idea of approximating the gradient? Because we still have to battle with this idea of backpropagation through time. So, like, you may know that, like, backpropagation through time, you have to have O of t memory for t time steps, because you have to persist these hidden states, and then you have to calculate the gradients for these hidden states as you backpropagate through time. So this is heavy memory burden, forces smaller batch sizes, really kind of poor GPU utilization. There are certain RNNs nowadays that can be parallelized a bit more, which is kind of better. But I guess the classic example of an RNN is that it takes a lot of memory, and yeah, that's no problem. Yeah, so the kind of idea here is that we want to approximate this process so that we don't have to do this backpropagation through time. There is a trick that they're applying here. There's kind of a discovery that they made that if a recurrent neural network converges to a fixed point in this thinking process of fixed points and equilibriums, we can avoid unrolling the state by applying the backpropagation in a single step at that equilibrium point. So once the network has kind of settled in that local equilibrium, we can take that state of the network, and then basically just backpropagate through that last step. That is at least an approximation of what backpropagation through time would have been for all of the steps, which is, I think, quite a neat idea. So the idea here is that the gradient paths are like output head, the final state of the H module, the final state of the L module, and then the input embedding. So this only really needs all one memory, which means basically we don't need to unroll through time. To make a connection here to these deep equilibrium models, how they work, this one-step gradient approximation, I don't know much about them. I've tried kind of understanding these equations a bit more. So I can sort of try and explain how I understand them, is that you can sort of think that during one high-level cycle, the low-level module repeatedly updates its state until the state, like ZL, will converge to local fixed points, like this ZL star. So you can see here that basically we repeatedly inserting the same input here to that function for the low-level module, which is ZL star, and eventually basically this describes a state where that has settled and is no longer changing. Yeah, and then we've got the similar thing for the H module. However, this one only runs once after all of the cycles for the low-level module have completed. So this is nicely kind of described here. I can try and make that a bit bigger in the pseudocode. So we've got this kind of outer loop here that will run through steps, and then we run the low-level module, and then every t, basically, which is defines the cycle duration, we run the high-level module. The interesting thing is that we don't capture the hidden representations here because we do torch no grad, which means we cannot compute the gradients for these time steps, which means we don't fill the memory with these hidden representations, and we only do this at the very last step, which is this last part here, that we calculate the low-level network and then the high-level network once again after this loop, which captures the hidden representations at that last point. And this is what lets us do this backwards pass here later. So kind of a neat idea that we only really care about the last step in the unrolled RNN, I guess. What they also talk about is this Jacobian here. I think what they're trying to get at is that you can approximate the gradients of this you can approximate the gradient of this final hidden state or the settled hidden state for the high-level function with this equation using this implicit function theorem. Again, I'm not fully well-versed how that works, but I think the key idea here is that this is expensive because you have to do a matrix inversion and you have to evaluate the matrix, which is, again, quite expensive. So they use another trick here, which is this Newman series expansion. And this basically boils down to the idea that you can approximate this again into identity, which then lets you plug all of this into these equations for the gradients. And eventually you can obtain the gradients for the high-level module and then for the low-level module by plugging that back into equation 2. So into this one. So basically what they're trying to detail here is that backpropagation through time can be approximated through various kind of steps. But the general gist is that the way this practically works is you just look at the last states of these RNNs, which, again, I'm not sure if they're RNNs because they look more like transformers than RNNs. So that's the basic kind of system. There's another few points that are really important for this system. One of them is this deep supervision. This, again, is inspired by kind of the operation of the brain, where we've got these periodic neural oscillations, as they call them, which they regulate when learning occurs in the brain. So they're trying to, I guess, simulate that in a way. So they try to incorporate that deep supervision mechanism into the hierarchical reasoning model. So the idea there is that we get like this data sample, XY, and we run the multiple forward passes of this model and calling each of these passes a segment. So for each of these segments, we then note down the final hidden representations of both the high-level module and the low-level module. So again, we only look at the last representations. And given the previous state component from the previous segment, we compute the next state. And then that gets outputted through the forward pass of this model here. We then calculate the loss, and then we update the parameters. And the crucial aspect of this procedure is that this hidden state is detached from the computation graph. So again, going back to this pseudocode here, you can see that they detached the final hidden state. And what that basically means is we don't have to calculate. The gradients are no longer dependent through all of the steps in an unrolled kind of backpropagation through time fashion, but they're only dependent on the last state of the networks. So that's again the crucial mechanism here. Nice. So that's the deep supervision. Then we've got another idea, which is adaptive computational time. Again, they're trying to kind of do another inspiration through the brain, how the brain works. So we've got the system 1, which is automatic thinking, and then another system 2, which is more deliberate reasoning. I'm not too sure. Potentially it can be applied to generic recurrent neural networks. Again, I'm not fully sure how they've defined the networks. They mentioned that they're recurrent networks, but they look more like transformers. So I would really encourage you to look into the code and how they're actually implemented, because to me they look more like transformers. But yeah, I might be wrong on that one. Yeah, so we've got another inspiration through the how the brain works, and we want to replicate that as a similar pattern in reasoning models. So they come up with this adaptive halting strategy. So by halting strategy, they mean at what point do we stop the reasoning? At what point do we decide to continue the reasoning? So the idea here is they use this idea of deep supervision and also Q-learning. So the Q-learning here is that we've got this kind of small Q head, that is trained together with the network. And it basically, all it has to do is give a score as to whether we should halt and whether we should continue. And it's kind of controlled via these two knobs called mmax and then mmin, which basically tell you how many number of segments can you maximally do or minimally do before you can even attempt to halt. The probability for mmin is also determined stochastically, which means it can sample from like between 2 is the minimum number of segments that this process will run, up to mmax, and this kind of stochastically encourages longer thinking, even on simple problems, which in a way regularizes the network in the training process. Yeah, so this is kind of probabilistic here. And yeah, the decision basically is made when the when this estimated hold value, so this Q, the score, exceeds the estimated continue value. So if the Q head thinks it's more beneficial to halt than to continue, then the decision is made against the minimum threshold. So I guess the scores could be explained as like, if I stop now, so that's for the halt score. If I stop now, how good is that? And then for the continue score is, if I think one more segment, how good is that as well? So then they define the targets in this kind of Q-learning Markov decision process system. So the GM halt and then GM continue. And what they're trying to do, what I guess the interesting thing that they adopted here is that they do the overall loss for this process is a combination of the loss for like the sequence to sequence training that they do on the actual network, plus binary cross entropy loss for this Q head. So in effect, what's happening is that both of these things are being trained at the same time. Yeah, so we compute the combined loss, and the idea is that like the model will learn what to predict, but also when to stop reasoning towards that prediction at the same time, which is actually quite a neat approach, I think. Yeah, so if we select halt, the action ends the supervision loop. Yeah, another interesting thing they've added here is that the sequences can be processed in batches in practice, which means that if you halt one of the sequences earlier, then that means you can substitute another sequence into the batch and continue. So you can sort of like sort in and out the different sequences as they halt. Yeah, so there's a performance comparison that they've done as well here. Basically, what they're trying to show here is this inference time scaling. And this is a very important part of the network or of the system in general, because you can increase or decrease the computation spent on reasoning using this mmax parameter. So if you set this really high, that means the model will, in theory, given only Q continue scores are being continuously produced by the Q head, in theory, that model can go up to the mmax of reasoning, which is quite a nice way of controlling how much time and effort and energy you can spend on reasoning on any forward pass. Yeah, so they note that for Sudoku, which often requires a long-term planning, this model is really strong in terms of this inference time scaling. So if you increase the number of computational steps, the performance on Sudoku will go up significantly, whereas for ArcAGI, it wasn't as significant. But what they show here is that if you use this dynamic approach to scaling of this compute time, then you can perform on average lower number of mean compute steps and achieve similar performance, which means it's actually quite an efficient system. Nice. So the next bit, I want to talk about. They talked a little bit about stability of this Q-learning. Normally, when you do Q-learning, you need like different stabilization techniques. We call them like replay buffers, target networks, but they're not in this design of this system. So this approach achieves stability as they say, through the intrinsic properties of this model and this training procedure, which means the way this is designed, it keeps the network and the training stable throughout. They provide some like backing as to why that is, and it's in part because they use like this post-norm architecture, which I'm not sure what that is, and the specific optimizer that they've chosen. So a little bit more about the architectural details of this. As I mentioned before, this is a sequence-to-sequence architecture, so we get a sequence of tokens, and then we get a sequence of tokens back from after the inference. And then we've got this embedding layer for inputs, kind of very kind of common approach. Then we get this output head, which is a softmax, which will transform the hidden states into token probability distributions. The loss is averaged across all of the tokens inputted, and the initial states are initialized. Initial hidden states are initialized from a truncated normal distribution. And they're kept fixed throughout training. What else is interesting about this? So both the low level, this is where I got really confused. So like both the low level and high level recurrent modules, the low level, the FL and the FH, are implemented using encoder only transformer blocks with identical architectures and dimensions. And that they also mention for these transformer blocks, they take certain parts or improvements from like Llama architectures, which, as far as I understand, are not RNNs, the transformers. So things like rotary position, I think there should be embeddings and encoding, like GLUs, RMS norm, removing the bias terms. Like all of these things are quite common in like more recent Llama architectures, which improve upon the kind of basic transformer. So they've adopted the same thing, but then they also say these are recurrent networks. So I'm not quite sure how and why. Nice. So results, benchmarks. So more specifically about what these benchmarks are, like the RKGI, as I said, is quite a popular method, and many conventional like deep learning methods and even chain of thought techniques, they don't do very well on this. It's very hard to generalize to new tasks, whereas this model actually did really well on this. It's like bypassed by even like 10%. The current state of the art, which is really good. They've got another one, which is Sudoku Extreme. So they've picked, I think, really hard examples of Sudoku like puzzles from different data sets. They've also generated some, I think, and then used that as the training and kind of validation set. But only a really small one, which is a downsampled subset of only 1,000 training examples. So you can see that this model also not only has small number of parameters, which is 27 million, compared to like huge number of parameters like billions in OpenAI or Claude models, but it also works in low data regimes, which means if you don't have a lot of training data, this model can actually learn quite a lot from even small numbers of data points. For these sorts of tasks. They've used a Sudoku solver to try and measure the difficulty of each puzzle by counting the number of backtrackings that the solver has to make for each puzzle. So if it has to backtrack a lot of times when it makes the guesses because they're incorrect, then that means that puzzle is quite difficult. They've also had another data set called Maze Hard, which is basically maze navigation and pathfinding. Again, 1,000 examples there for training and then test set. Anything else here to point out? I think majority of the actual results are shown at the beginning of the paper. So here, I'll make this slightly bigger. So you can see that for like generally around 1,000 training examples for RKGI 1 and 2, it's really like outperformed the previous states of the arts on a very hard reasoning benchmark, RKGI. And then for Sudoku, it basically beats everything out of the water, like 55% accurate versus 0 on like even the large models here. So some really cool results if to trust them. Yeah, and that's basically the paper, I think. They talk a little bit more about like visualizing the time steps, how long it takes to converge to a fixed point. I don't think they do. There are like I've had a look at some of the issues on GitHub for this code, and people are saying like long training time, like there could be up to like 100,000 training iterations for 1,000 sample data sets. So maybe the training time is actually the blocking factor here. But yeah, it'll be larger because you have to perform a lot more forward passes in each of these kind of cycles, as you say, under the deep supervision, which means yes, it'll be taking a lot longer to actually go through one iteration. So yeah, I guess that might be the the negative factor of this model, is that yeah, it takes a lot longer to actually train it. But yeah, it's kind of cool how different problems like the ArcAGI, this is the pathfinding, this is the Sudoku, and then ArcAGI, how they all have slightly different ways in which the model approached solving the problem. So for like these maze ones, so explored like certain paths, so you can sort of see blue dots every now and here. So basically trying different things, and then eliminated some of them, eliminated some of them that are basically like blocked or inefficient, and then it constructed the preliminary solution, and then it basically tried to iterate over it to fix it, like here, for example. Sudoku were a bit more like a depth first search, so it had like exploration of different solutions and then backtracking. And then ArcAGI was more incremental, actually. So it iteratively improved upon the solution. So you can see that here, for example, where the test input was like this, and then it iteratively tried adding more and more towards the solution to make it kind of in line with the example inputs and example outputs. The question was, did they also test on other benchmarks like math and code? No, this is purely on ArcAGI, these three benchmarks. It has nothing, I don't think they've attempted anything to do with like actual language abilities. This is definitely not like a world model or a large language model. It's a model that is specifically trained to solve puzzles like these. But I guess the neat thing about it is it shows the reasoning pathways, is that the reasoning is focused on these puzzles, but there was no pre-training or fine-tuning on actual language like wiki text or math benchmarks. There's nothing like that. So a lot of claims that this there are a lot of claims in this paper that this model can be revolutionary, but they've not really tested that as far as I understand. Yeah, there's some additional details here about how that actually corresponds to the brain and how the brain works. I know very little about neuroscience, so I can't really validate any of this or even comment on it, but I'll leave it up to you to kind of read this if you're interested. Yeah, I guess they can validate that. What was it? I was reading this yesterday and I can't remember exactly why I highlighted this. Yeah, never mind. But yeah, some more stuff about related works. How they've got like the reasoning, chain of thought is mentioned, A-star kind of pathfinding and search, and they compare this adaptive computational time to this. More stuff about how like different architectures are brain inspired, and then how hierarchical memory works. Some more discussions and conclusions, and there was no appendix in this paper. So yeah, that is the paper. So I'll leave it up to you for some questions, discussion. It'd be cool to discuss what you think.
Thank you very much. I thought that was a fantastic paper. And the fixed point iteration is quite smart, right? Because you sort of can decouple to some extent the lower lying tasks pretty much entirely with some approximation, but yeah, it makes the it's almost like sampling your updates, which is cool.
Yeah, exactly. And I think like even though it's an approximation, I think they've shown that it's good enough to learn something.
Exactly.
Yeah.
I did some Googling, and I think that, if I'm reading it correctly, there is some comment on the paper that when the difference between the test set and the evaluation set is for each problem is quite small. Like each environment they test the model on is quite narrowly defined, like Sudoku.
Oh, I see.
Do you know what I mean? It's not a you're not moving very far in distribution from or you cannot move very far in distribution from a test set, from training set to a test set.
Right.
So
I guess it wouldn't work the way that like you've learned on Sudoku and now suddenly you're going to generalize into ArcAGI or something like that.
correct. And ArcAGI you've learned on ArcAGI, and they train on all the training samples and then test on all the and then it's so I mean that's perfectly reasonable what they've done. So it's more a question about the generalizability.
Yeah, I agree. I think the only I think saving grace for this is like this small number of parameters. So
absolutely.
Isn't it also something that is quite generically true for IQ tests? That that's something you sort of can actually practice?
Yes.
Yeah, exactly. So maybe the idea that we're trying to test these models on Arc is not the right approach.
Yeah.
Thank you. Really good paper.
Yeah. Thank you.
Any other questions, comments? Cool. In that case, I think we can finish 5 minutes early and everyone get Philobos time back.
Awesome.
Thank you so much, Damian.
Thanks a lot, everyone, for coming.